No? All right. So we're going to take a look at 1.1 and 1.2 today. They're shorter sections. They're very introductory, and we're going to use a lot of this language as we continue on in the course. So the main focus for today is really about some of the vocabulary that we're going to be learning, and also what the main point of this class is, okay? And so if we start over here with what we know, that's sort of a typical format that I like to start the notes with, because I think no matter how complicated things are, everything that we're learning goes back to something that we've learned in the past, okay? And it's about making those connections so that we understand, like, okay, we do know this, and maybe feel more confident walking in. All right, so what do we know? Let's say we have an equation like 2x plus 7 equals 9. What would you expect that I ask you about this particular question?
Solve for x.
Oh, exactly. Solve for x, right? Find x. And so what would we do if we wanted to solve for x? And again, folks can type in the chat, you can unmute, whatever way you feel best is a safe way for you to contribute.
We could put variables on one side and constants on the other.
Good, good. Yeah. So let's isolate x by subtracting 7. Gosh, it's been a long time since you've seen things that maybe look like this, huh? And then divide by 2. Good. And so we'll get x equals 1. All right. Perfect. Perfect. And so we've known for a very, very long time that we can solve a linear equation. All right. And we know, how do we know that this is linear, by the way?
X is to the power of 1.
Yeah, that x is to the power of 1. Okay, and so that's how we defined a linear function. And we knew that linear functions have one solution at most. All right, what about the second equation that we have here? X squared plus 4 equals 5x. I'm likely asking you to solve for x again, but our strategy might be a little bit different. How would we approach this one in terms of solving for x?
Probably have to set it equals 0 and then probably factor it.
Yeah, so let's do that. Really good rule of thumb. You see a quadratic, setting it equal to 0 and factoring is probably a really, really good first step. Okay, so setting that equal to 0. It's probably been a while since you factored, depending on what classes you've taken before. So if you're coming fresh from discrete and linear, it's probably been a while, but factoring is probably an important thing to, always have in your back pocket. So we factor, we get something like this, and we end up with not 1, but 2 solutions. Okay. Now, how did we know that this was a quadratic expression or a quadratic equation? What told us that?
X squared.
Yeah, exactly. That x squared told us that it was quadratic. Okay, and this first degree here, the invisible one, told us that it was linear. All right, so hopefully this was a nice little review in terms of things that we know. But as far as what's new, we're going to be taking a look over the entire summer session at things that look like this, okay? And for all of these types of questions, our goal is going to be to say, what does y equal? Okay. So this whole summer session, we're going to be looking at solving equations. Now look at this. They have a derivative in it. So here we have our y prime, that's a derivative. Here we have dy dx, that's like another way of saying derivative, right? And the last one, we have y double prime and y prime. And so we're going to be looking at a lot of different types of these equations that involve derivatives. That's why we call them differential equations. okay? Because all of our equations will have dy dx or y double prime or some sort of derivative in there, okay? Now, how do we get rid of a derivative? This will be maybe a throwback to like Calc 1, maybe Calc 3. How do we get rid of a derivative?
Take the integral.
Yeah, exactly. So we are going to be looking at undoing these with integration. Okay, so lots and lots of integration, especially in this first unit. Now, I know that the flow of the courses that we take here is sort of weird because we haven't seen a ton of integrals since Calc 3, right? And maybe not even since Calc 2. And so it would be really important for us, especially this first week and first and second week, to be going back into our derivatives and our integral rules to really make sure we've got them down pat, okay? And in particular, I do want to note that we're going to be using U sub integration by parts, partial fractions. So I think those are sort of the three main ones that come up again: U sub, integration by parts, and partial fractions. So those will be ones that if you're like, ooh, I haven't seen those in a minute, you might want to spend more than a couple minutes this week looking over U sub, integration by parts, and partial fractions, okay? All right, but before we get into all that nitty gritty, let's back up and talk about some definitions, right? So a definition, a differential equation is an equation that contains the derivatives of one or more unknown functions. Now, these derivatives all happen to relate to that dependent variable. And we're also going to be incorporating one or more independent variables. And so in other words, we're going to have a lot of x's and y's, y primes, maybe some y double primes, and we're going to be trying to get y all by itself. Okay, so that is our end goal. And so to that end, especially for those of us who might be math or applied math majors, maybe some engineering as well, there are sort of two typical classifications of differential equations, okay? One of them is called an ordinary differential equation. And so we tend to abbreviate this as ODE, right? Ordinary differential equation. And then there is a class of differential equations called partial differential equations, which we usually write as PDE, okay? For those of you who are at state, or if you're thinking about going to state, I believe this is 531. And this is 537 at state. But they are typically 500 level classes where you dive a little bit more deeply into one of the two types of differential equations. Now, what we're going to be doing in this class, we are going to be focusing on getting a really good ordinary differential equation foundation, okay? All of that will be important. If you ever choose to take partial differential equations, you'll still use a lot of our ODE knowledge to do that, okay? And so what do these things mean? An ODE is an equation that contains only ordinary derivatives of one or more unknown function with respect to a single independent variable. And so here are a few examples of what that might look like, okay? So you might see something that looks like this: dy dx plus 5y equals e to the x. That would be considered an ordinary differential equation, okay? It's ordinary because this derivative, dy dx, is ordinary. You might have something like this too. Maybe you have dx dt plus dy dt equals 2x plus y. That could be another example of an ordinary differential equation. And it's ordinary because we have dx dt and dy dt. And we might have some that look something like this. So d squared y dx squared minus dy dx plus 6y equals 0. We will also be figuring out how we solve things like that. Okay. Well, what makes a partial differential equation partial? Well, it doesn't contain ordinary derivatives. It contains partial derivatives. Okay, it contains partial derivatives. And so what that might look like is maybe something like this. Okay, so that should be familiar from Calc 3. And in fact, whoops. You might see a lot of partial derivatives, okay? So if you take partial differential equations, you'll see a lot of partial derivatives and figuring out how to undo those. Another example of a PDE might be partial u over partial y equals negative partial v partial x. That might be another type of partial differential equation. But we're not going to worry so much about that, okay? So, but if you are going to be taking partial differential equations, really important to brush up on Calc 3 stuff. But we're going to be focusing on the ordinary differential equations where we'll focus more on Calc 1 and Calc 2 stuff, okay? All right, so it is important, just like we could look at those equations we saw earlier and say, this one is linear, this one is quadratic. We want to be able to classify our differential equations by order as well, okay? So we're going to be able to classify them by order and then something called linearity. Well, what does it mean to classify something by order? The order of a differential equation is dictated by the order of the highest derivative. So we're going to look for the highest derivative in the entire problem, and that will tell us the order. Okay. And so let's zoom in a little bit here with our example number 1. Where is our derivative, first of all? Where is the derivative located? Yeah, that dy dx, right? This is our derivative. And would we say that's a first derivative, second derivative, third derivative? What would we think? First derivative, right? So this is we could call this a first order differential equation. Okay, so if someone says, what order is that? You look for the highest derivative, and that will tell us what order it is, okay? What about example 2? Where is the highest order derivative?
Y double prime.
Yeah, that y double prime. So we're going to call this not a first order, but a second order. Okay. What about the third one?
Third order.
Yeah, that's going to be third order because we've got this partial one. So we're not going to be solving ones like this, but that would be for that other course, partial differential equations. So we could consider this a third order. And what about that last one, example 4?
That'd be third order.
Ah, okay. So this is a little tricky because sometimes the notation, like we have these primes, but beyond a certain number, sometimes they turn that into an actual number, okay? And so it's not all textbooks that do this, but some do say like after 3, they just change that to an actual number, okay? So this one we could actually consider as a 4th order. But I'll make sure that I'm very clear on that. We're going to spend more of our time working on 1st and 2nd order ones, but sometimes notation can be tricky in a math class. So that would be a valid question to ask any future instructors. Okay.
So in the future, where there's not gonna be a time where we have like the differentials with the exponents. Like
Oh, you mean
yeah.
like both a power and the
Yeah.
Yeah, I think that tends to be more clear. Most of the time, I think that's why folks write like the y triple prime, but it's also why people write it this way, because there's a lot less question about which derivative it is. Okay.
Okay.
And William, that's a great question. So that's why I just wanted to show, I think in this case, you're right, it is ambiguous. So if I tell you it's 4th order, I just want us to be aware of that notation. And I would not have expected you to know that from the context, but I think it's a valid question to ask, if that makes sense. So it's more to point out, if you're not sure, sometimes it's worth asking about the notation. Okay. All right. So another way that we can classify differential equations is by something called linearity, okay? And so earlier, I gave us an example of a linear equation, and we knew that it was linear because that power was 1, right? So if we scroll back up to our what we know, we knew this was a linear equation because there was a power of 1 there. We knew this was a quadratic because that's a power of 2. And it turns out that we are going to write the linear differential equations. We're going to look at a general form, but we're going to be looking for different things to know that it's linear. Okay. And so let's go back to this. A linear differential equation can be written in the following form, okay? Now, I'll go ahead and write this out, and we'll talk about what each thing means. So we start typically with some function of x, and then we have a corresponding derivative to that same term. Okay, so if we're looking at a 3rd derivative, right, then we call this the coefficient for the 3rd derivative. And we kind of keep going. So, and we're going to lose 1. And then this derivative will lose 1 power. All right, so we start with the largest power or the largest derivative. And we kind of keep going all the way, right? That's what those ... dots mean, all the way until we get back to like our 1st derivative. And then just y. Okay. And all of this we typically say is equal to g of x. And I know that's a lot of writing, but I wanted us to make sure that we could kind of see the structure here. And the main idea is that we're moving from the highest order derivative to the lowest order derivative. Okay. Now, how do we know that this is a linear differential equation? Well, there's 2 things that tell us that it's linear. The first thing is that the power of all terms involving y. So any term that has y in it has a power of 1. Right? And we'll see a couple examples of this in just a little bit. All right, but any term that involves y has a power of 1. And I don't mean a derivative, I mean like a literal power, okay? The second thing we're looking for is that the coefficients depend at most on x. Meaning like this a sub n of x, a sub n minus 1 of x, a sub 1 of x, a sub 0 of x, those only have x's in them. Okay, they only have x's in them. And so let's write down some examples of linear versus nonlinear ODEs, okay? So a linear ODE, we could maybe write something like this. Okay. So how would I know that this is a linear ODE? Well, I would look at my checklist here. First thing I'm going to do is look at all the terms involving y. Is that power 1? And so if I look at the left-hand side, I notice I have a minus 5y. What's the power of y? Well, that power is 1. And so we've got our first one. We can say, yes, the power of all terms involving y is 1. Okay. Now let's check the second thing on our list. The coefficients depend at most on x. Where are coefficients? X cubed, x, 5. All those coefficients only involve x. Okay, so we're
So
looking.
for coefficients, you mean anything, the coefficients just for y, right?
The coefficients would be any of these things in the front.
Yeah, but like if we were to have, I don't know, 5x, yeah, just 5x, that wouldn't be,
Oh, like this is not a coefficient.
no, I don't know how to phrase it, but yeah, maybe when I get the right words, I'll ask again.
Okay. It's okay. It takes some time for like us to figure out phrasing, but for me to understand what folks are asking as well. Okay, so but let's maybe give a second example and see. So something like this would also be considered a linear differential equation. So y double prime minus 2y prime plus y equals 0. Okay. So in this case, what is the coefficient function of y double prime? Yeah, it's just a 1, right? There's an invisible 1 here. And so what that means, if I compare it to the earlier notation, is that my coefficient function is 1. Okay, the coefficient function for y prime is -2. And the coefficient function for y is just 1. Okay. That satisfies all the coefficients being dependent on at most x, because I don't have y in there. It's just a constant 1, -2, or +1. Okay. Now, all of the terms involving y, well, there's only this one, and that one has a power of 1, so we're good to go. All right, both of these examples satisfy this checklist over here. Well, what might be an example of a non-linear or ordinary differential equation? So here's one. Okay, and I think this notation, William, would be how I would prefer to ask for a fourth order, because I think it's much less ambiguous than that 4 to the x or the y to the 4th power. Okay, so if I were to ask for a fourth order, I would probably write it like this, so it would be much more clear. All right, but what about this equation makes it non-linear?
Y squared.
Desired in the power of 1.
Exactly. So this right here is not 1, so non-linear. Okay.
Professor Judy,
Yes.
what if you had an x in front of the y squared?
Well, that would be okay.
So would it be considered, so if it wasn't a y squared and if it was just a y and it had an x in front of it, it would be a linear differential equation?
Yes, absolutely. Absolutely. In fact, let's write that down, that this is not the part that makes it nonlinear. And if we did this, then that would be considered linear. Exactly.
Okay,
Power of 1, coefficient has at most x in it, we're good to go.
how about if it was like x squared?
X squared would be
Fine.
okay. That
It
would
would
be.
be okay, okay.
Mhm. Yeah, so we're looking for different pieces of this, right? It's not as straightforward as it is when we look at like a regular linear equation anymore. All right, let's give one more example of a non-linear one. Whew, that's a lot of letters, all right? But welcome to the next 8 weeks of your life. Lots of letters like this. Let me make this a little bit more clear. This is a d squared y dx squared. Now, this is non-linear, but I'm wondering if we can identify the features that make it non-linear.
Is it just a y squared again on the third one?
That is one clue, because this could be considered part of that function, okay? But I would say more than that, we could actually consider all of this to be the expression that we're looking at. What else tells us that this is non-linear? There are a few other indicators.
This is a trick part.
Exactly. There's a trig, but look at the letter there. It's not sign X, because that would be okay. It's sign Y. All right. And so just like we have in the chat right here, the coefficients depend on Y. So since all coefficients depend on Y, we consider this non-linear. Okay, so coefficients depend on Y, not on X. All right. Now, the classification, to be honest, is not the most important thing for us in this course, all right? But if you decide to continue on in your math education and look at like ODE or PDE classes, classification can be important because they'll tell you how to solve a problem, all right? So I wouldn't get too tripped up on the vocabulary here, but I think it's good to be familiar with what these terms mean, okay? All right, so let's talk a little bit about solutions, all right? So we've talked about what the question looks like, but now we need to think about what the answers will look like, all right? And it turns out, like we said earlier, that the solution of an ordinary differential equation is basically gonna be some function. All right, so our answer is not going to be a number like we got before we had like x equals 1 or x equals 4, but our solution is actually going to be a function. And that function will tell us if we plug that number into the equation, or sorry, if we plug that equation, our function into the equation, then we'll actually get an accurate thing, something that makes both sides of the equation true. Okay, so before we try one of these, let's go back up to the top for a moment. All right, if you think back to your elementary or middle school days and your teacher said, solve this equation. And then next to it, there was probably a box that said, check your answer here. And when you went to check your answer, all you did was you took your equation, right? So this was the original question. And everywhere you see your letter, you plug in the number you have. So you get 2 times 1 plus 7 equals 9. You get 9 equals 9. And your little middle school self was like, yay, I got the question right, right? Because it worked out when you plugged it back in. And so one of the things that we do a lot in differential equations is we take a look at our possible answer and we plug it in to make sure it works. So it almost feels a little bit backwards, okay? But what we're gonna call that now, we're gonna call this idea verifying the solutions, okay? So I'm gonna say, here's the solution. I want you to show me that it's true. And what you're going to do, you're going to take that solution, plug it into the equation, make sure you get something equals itself, and you're good to go. Okay. So let's go back down to Roman numeral 5 here. All right. So these solution functions, typically we call them y of x. They're going to be defined over a certain interval, and we need to make sure that these functions are indeed continuous. Otherwise, we can't take all the derivatives of that. So we sort of make the assumption that we're looking at something continuous. All right. As far as notation goes, some textbooks use y of x, and some of them use phi of x. All right, so it just kind of depends on the text or on the questions. Our textbook uses y of x a lot, but as you move into upper level classes, you might replace that with a phi of x, but it's the same thing. It's just your solution function, okay? Now, one method that we can use to verify a solution is, and let's write this down, substitution. Okay, so we can use substitution to make sure something is true. But we have to have something to substitute into. And so in this case, in example 5, the question is y of x equals x to the negative 3/2 a solution for the differential equation given here? Okay. So here's what we're going to do. If we are going to verify the solution, we need to be able to plug things in to the left-hand side of this equation. And when we simplify it, we should get 0. So what can I substitute in right away? I know that y, or y of x, is x to the negative 3/2. And so what that means is everywhere I see a y, I can replace that with x to the negative 3/2. So right over here in that green, I'm going to put x to the negative 3/2. But I have some other things to substitute. For example, I have this y prime here. How do I sub in a y prime? And how do I sub in a y double prime? What are
Are we gonna have to like maybe integrate those or to get it to like a y? Like say, first derivative, just integrate it, and then the second derivative, integrate it twice to get it there.
So starting tomorrow, we're going to learn some techniques on how to do that, right? So we can integrate and find an exact answer. But since we don't know how to do that yet, check out what we can say. Since we know y, can we find y prime? Well, if I want to find y prime, all I need to do is take that derivative, right? So how long has it been since you all have taken a derivative? Like a while, huh? I think we're just using the power rule here. So as a refresher, if I want to find that derivative, I'm going to bring the power down to the front, keep the variable, and I'm going to lose a power. All right, and if I clean that up, I'm going to get -3/2 x to the -5/2. Yeah. Guess what I can say with this? Everywhere I see a y prime, I'm going to replace it with that. All right, help me out. How do we find y double prime?
You would take the derivative of y prime.
Take that derivative again, exactly. And whatever we get there, we'll be able to sub in to that y double prime in the original equation, okay? So we take a derivative again. 3 times 5 will give me 15 over 2 times 2 is 4, x to the -7/2. And so everywhere I see y double prime, I'll replace it with this, okay? So we're going to take all of this, we're going to plug it into that. And let's see, 4x squared, 15 over 4, x to the -7/2, plus 12x times -3/2, x to the -5/2, plus 3, x to the -3/2, and we hope that equals 0. Right, so this is just our substitution, our y prime substitution, our y substitution. All right, seems like a good time to work through some algebra and rules again. So I'm multiplying here, this 4 and that 4 reduce. So I should end up with 15x. And let's figure out the power of the x. I have an x squared and an x to the -7/2. What do I do with those exponents? Add, subtract, multiply.
You would add.
Yeah, you would add them. And so 2 minus 7/2, that should give us -3/2, I believe. All right, so let's keep going. We're going to get, let's see, 12 divided by 2 will give me 6, and that will give me -18 x to the -3/2, because same thing, I add those exponents. And I finish off with a plus 3x to the -3/2 equals 0. And when we add up all those coefficients, it turns out these are like terms, and we do in fact get 0 equals 0. Okay, so this is a more grown-up version of what we used to do in middle school to check our answers. In order to say, is this an answer, we just plug it in, take the appropriate derivatives, and we should make both sides equal to each other. Okay. So any questions about verifying the solution?
What do you mean to verify a solution?
Exactly what we did right here. So if I say verify a solution, I expect you to take the solution, find the appropriate derivatives, and then plug them into the differential equation. Yeah?
Thank you.
Okay. All right, so let's try one more, verify the solution, okay? So if you look at this question, it says verify that y of x equals x to the -1/2 is also a solution for the differential equation, right? So this is a great chance for us to practice in the privacy of our own learning environment right now. Why don't you go ahead and try setting this up using instead y of x equals x to the -1/2. Okay, so I'll give you a moment to get a head start, and then I'll start putting my work down here. All right, so hopefully these derivatives with the power rule look very similar to what I have on the screen. You should always feel free to say, hey, Judy, I think you made a mistake. I don't think I did right here, but it happens. So if you think that my answer is incorrect, please let me know. We don't want to document things that are not right on video that last forever and ever. All right, so let's see what happens when we plug in this time. And hopefully you're arriving at something very similar to what I have here. That we have applying the product or the power rule, plugging things in, making sure we're accurate about our computations. We end up with 0 equals 0, which means that lo and behold, we actually have two possible solutions for this differential equation. Okay, two possible solutions. Now we're going to spend a lot of our time looking for specific solutions, because how do we know which one we want? That's why we're going to use all the techniques we're going to learn in the next few weeks to figure out, well, which one is the appropriate solution that we're looking for. Okay. So when we say verify, this is the process that we're looking to do. All right. All right, we have one more example here of verifying. We're not going to go through this one, but I'm wondering if you can help me set this up. Okay, so y equals x e to the x. If I want to find y prime, what rule do I need to use? Yeah, and so I would say product rule, right? We don't need chain rule for this one, but we will need product rule. All right, so I'll leave you to do that, to take that first derivative. And we are going to need product rule to find that second derivative as well. Okay, so as you are working through these, I've chosen these problems to sort of reintroduce our brains to all things derivatives, right? Because we're going to spend a lot of time on derivatives, but also on integrals. But I'll leave this for you to complete as an exercise on your own, but this should be a solution. Okay, so at the end, if you can't make the left side equal the right side, then something went wrong here in your derivative. Okay. All right, so that's it for 1.1. All of like the notation and what does it mean to verify a solution, okay? And so in the last 10 minutes or so of class, what we're gonna talk a little bit more about initial value problems, which is a specific kind of solution that we're looking for, okay? All right, so initial value problems. This list on the left-hand side will be sort of a running list of what we know. So we know hopefully the difference between an ODE and a PDE, how to determine the order, whether it's linear or non-linear, and how do we verify solutions. But the question we want to ask ourselves in this section is, well, we have so many solutions. How do we know which one we want for a specific problem? Okay. And so we're going to take a look at this. Solutions for initial value problems. So in this previous lesson, we saw that there are so many solutions to this. How do we know which one? And we only worked through 2 of them, but here are some more. If you want to practice verifying your identities, you can use these as extra practice, okay? But what we want to note is that when we want to find a specific solution, we have to apply these things called initial conditions, okay? Initial conditions. So usually the way we write this is we'll have our differential equation, and then we'll have some initial conditions, all right? Initial just means at some time that we want, what is happening, all right? It doesn't always mean that it's like y of 0. It just means that at the moment we want, what is happening, okay? Now, what I'd like us to do with this one is take a look at the question that we've been looking at, that same differential equation. And what we're going to do is see whether these things are true, okay? So you have your y of x. We know that equals x to the negative 3/2. And so all we're going to do is we're going to grab the appropriate initial condition and make sure that it fits, okay? And so of these 2, we want to use the first one and see if that's true. So y of 4, it would be 4 to the negative 3/2. I could write this as 1 over 4 to the 3/2, which I can write as 1 over the square root of 4 times 4 times 4. But all of this is just a really fancy way of saying 1 over 2 times 2 times 2. Gives you 1 over 8. Give yourself a check. You have verified that these initial conditions fit this problem. I'll leave the second one for you to verify on your own. You'll take that first derivative, and this time you're going to plug in y prime of 4 equals negative 3/64. Okay, so you're going to plug in a different number this time. It should work out, but it's a good chance for you to practice that algebra there. So I'll give you time to do that on your own. All right, so let's take a look at some of these other ones, okay? So verify that y equals x cosine x is a solution to the initial value problem here, okay? So we are gonna use some trig as well, which is why I'm trying to throw that in there earlier rather than later, all right? But if we were to go ahead and find this initial value, all right? So we're gonna do one thing first, and that is we have y, which we can substitute in here, but we're gonna need y prime as well to substitute in on the other side, okay? So I have y equals x cosine x. What rule am I going to need to find that first derivative?
Product.
Yeah, we're going to need product rule again, okay? So we'll get x times, what's the derivative of cosine x?
Negative sign.
Yeah, negative
X.
sine x, good. Plus 1 times cosine x, which will give you this. All right. So this I can plug in for that y prime part. Negative x sine x plus cosine x equals cosine x minus y tangent x. And what can I put in for the y? I can put in the x cosine x Ooh, some of that trig stuff. It might have also been quite some time since you've seen trig, but we can certainly simplify this because we want to be able to match both sides, right? And so we have this minus, let's see, x times cosine x. Another way to write tangent x is sine x over cosine x. And we notice here that if we reduce, we'll end up with the same thing on both sides, okay? I will leave, for the sake of time, this for you to verify. So verify this initial condition. And you can do that by plugging numbers in to your equation. All right, so you can do that by plugging numbers in to your equation over here. I think it'll be a good reminder of like, where do we get all those trig values from again? All right. So in the last 5 minutes here, we're going to finish this example number 3. All right, so we've got a differential equation, x double prime plus 16x equals 0. What order is this? I would say what order? What would you say?
Second order.
Yeah, we've got a second order here because it's that x double prime, okay? So if we want to verify this, I have x, I need to find x double prime too, so I can substitute that in, okay? So x prime of t, what do we get when we take the derivative of this first term? C sub 1 cosine of 4t. Maybe a better question would be, what rule do you need here? And we can assume that C sub 1 is a constant. Yeah, now we're going to need chain rule, right? So when we take this first derivative, we'll end up with negative 4 C1 sine 4t. And when we take the derivative of the second term, we'll get plus 4 C2 cos 4t. Okay, that's our first derivative. Well, we need the second derivative. When we take that second derivative, we better use chain rule again, okay? And it would be really important to just be careful about our signs here. And so what do we end up with? We end up with negative 16 C1 cosine 4t minus 16 C2 sine 4t. Okay. Now that we have those, we can plug those into the original differential equation and just make sure that it zeroes out, okay? And so we'll get negative 16 C1 cosine 4t minus 16 C2 sine 4t plus 16 times the original one. And I think one terminology that you'll hear quite a bit is, by inspection, this is true. And as inflated as that sounds, as like maybe very, highbrow as that sounds, we can sort of tell that this negative 16 C1 cosine 4t is going to cancel with that one. That'll go to 0. And similarly, this negative one will reduce with that positive one. And so we'll get 0 equals 0. Okay. Now we'll actually save this part for tomorrow. Okay, so we'll save this last part for Tuesday. And we'll use that to kind of launch our discussion into what it means to find a specific solution, okay? But we'll talk about that tomorrow. As far as today, we are done for the content today. So I'm going to go ahead and stop the recording and stop sharing my screen.